Hey guys, it's Miss Johnson and I'm here to bring you our notes for the first part of section 11.2. Today we are going to do a significance test for a difference of means. So just a reminder, we did this for a difference of proportions as well, and now we're going to do this for a difference of means. When you are writing a hypothesis for your difference of means, you're looking at mu1 minus mu2. That's where your null hypothesis is. So you're going to test this against 0. You're testing the fact that they're not different and trying to show that they maybe, in fact, are different, okay? So your null hypothesis is always going to be mu1 minus mu2 is equal to 0. Your conditions are still present. You got to show that it's random. You got to show the 10% when you are doing sampling, and you have to do the normal large counts for things that are less than 30. You draw a graph. All of that stays the same. So let's just practice testing those two things, writing the hypotheses and checking the conditions. So this first example, it says, has the mean number of hours Americans work in a week changed? One of the questions on the general social survey asks respondents how many hours they work each week. Responses from random samples of employed Americans were recorded from 1975 and 2014, and they are summarized here. So you got a row for 1975 and you got a row for 2014. Okay. Do these data give convincing evidence at the alpha 0.05 significance level of a difference in the true mean number of work hours per week for Americans in 1975 and 2014? State the appropriate hypotheses for a performance and significance test. Be sure to define the parameters and then check the conditions. Okay, so this is what you would be given if this were an AP exam. That's all you'd be given. You wouldn't be asked these specific parts here. You need to know that those are things that you have to list. So let's take a look at our two means here. So we want to test, so for part A, this is how I would write this out. We want to test the null being the mean for 2014 minus the mean for 1975. And I'm just going to subscript them that way so that I can keep the two straight. You could call this mu1 and mu2, and then you do mu2 minus mu1, whatever. You can call them whatever you want, but I'm just going to put the years with them because I think that helps me. And I'm testing the fact that 2014 minus mu from 1975 is not equal to 0. It says, is there a difference? Okay, do we have convincing evidence that there is a difference? So that's why I'm doing not equal to. My parameter here, you've got two parameters to list. So where mu from 1974 is the mean number of hours worked by Americans. This is supposed to be 1975. Sorry, I said 74. 1975 by Americans. And mu 2014 is the mean number of hours worked by Americans. I should have said in 1975. Mean number of hours worked by Americans, I'm running out of room, sorry, in 2014. Okay, great. List your two parameters. Hopefully you can make them a little bit more legible than mine are. I didn't have quite a whole lot of room there to write those out, but hopefully that makes sense. Basically, you need both parameters listed. Let's talk about B. Check the conditions. So for B, my conditions are random. We have two different random samples that were selected, and they are independent of each other. So independent random samples. Of 764 working Americans in 1975. And 1,501 working Americans. That's supposed to be capital A, sorry. Americans in 2014. Okay, so randomness, check. Then 10%. 764 and 1,501 are both less than 10%. Both less than 10% of all working Americans. In 1975 and 2014, respectively. Okay, and then the last one, normal large counts. This one's easy because we have big samples. So this one's good. 764 is greater than or equal to 30, check. And 1,501 is greater than or equal to 30, check. All right, so our conditions check out. Perfect. So all those conditions are still present when you're looking at a significance test for a difference of means. It's just that you have to list some of these things twice. Like, for example, I've got the 2 different large counts here for both samples. I have to list both parts being less than 10%. I have to talk about both being independent random samples. All right, so here's our test statistic. It looks similar to what we've always done. This piece right here is what it's always looked like. This is always your equation. So the test statistic is the statistic minus the parameter divided by the standard deviation of the statistic. It just so happens that in this case, the statistic is the difference in means. The parameter is the fact that there is no difference, so that would be 0. And then your standard deviation piece in the bottom is that sample size 1 squared divided by n, 1. Sample standard deviation 2 squared divided by n, 2. And this is a t test statistic, okay? It says when normal large sample condition is met, we can find the p-value using a t-distribution with degrees of freedom given by either technology or the degrees of freedom of the smaller one. Now, this is where we talked about this in class a little bit. This is an outdated practice, okay? This is going to be your preferred method, especially when you're putting 2 samples together, because it's going to calculate a degree of freedom based on the 2 samples together, and it's a degree of freedom that you wouldn't normally think. This using the smaller one of n-1 or n2-1, that's kind of an outdated practice going back to the table. So you're going to have a better option, a more accurate result if you use your calculator. Okay, so now let's actually look into some of these things. So it says refer to the preceding example. The table summarizes the data on hours worked from independent random samples of working Americans in 1975 and 2014. Explain why the results give some evidence for an alternative hypothesis. Why test? Okay, that's what's happening in A. That's what they're asking. Why would we test this? Then in B, calculate the test statistic. And then in C, what conclusion would you make? So this is like your do statement, and this is like your conclude statement. We already did the state and the plan. We didn't state the test necessarily, but we checked the conditions. So, all right, so let's take a look at part A. In part A, the question is, why do we test? So if I take a look at mu from 2014 minus the mu from 1974, I get 41.91 minus 38.97, which is equal to 2.94, okay? So the difference in the means is not 0, which is why we would test this in the first place. Not 0. We have, I should say, the difference in the sample. I should have put that word sample in there, sorry. The difference in the sample means is not 0, which is why we would test in the first place. All right. So let's take a look at part B. Now we're going to do the actual test statistics. So in part B, I have, this is just practicing using the formula. Mu of 2014 minus mu of 1974, we already did this, is 2.94. So my t-test statistic looks like this. 41.91 minus 38.97 minus the parameter of 0. We're testing against the fact that they are the same. The standard deviation in the bottom is going to be 13.13 squared divided by that 764 plus 14.35 squared divided by that 1,501. Okay, so go ahead and type all that into your calculator and you end up with a t-test statistic of 4.88. That's a really high test statistic. That's a lot of standard deviations away from the mean. 4.88 in terms of the number of standard deviations. You got to remember that 99.7% of our data falls within 3 standard deviations. This is almost 5 standard deviations away. So here's what happens. You get a p-value here of 0.0000116 when you do that out. The degrees of freedom that I got is 1,660.58. Now, I want to talk to you about where I typed that into my calculator. So in my calculator, I went to stat and then over to tests. And then under that, I did a 2 sample. It says 2 samp t test. For me, it's option 4. Okay, and then I typed in the stats, not the data, because we don't have the data. We obviously don't have all, of the respondents' individual data scores, but we do have the statistics just from this. Okay, so the statistics that we need were given to us in the table. So then you'd type in the stats and you'd hit enter, and these are the values that I got in the output. You also get this value out as well. So even though I showed the formula with the data in here, my test is going to give me, in my calculator, is going to give me the t-score, and it's also going to give me the p-value and the degrees of freedom. Let's talk about option C, or part C here. Obviously, we have a very low p-value. So for our p-value, our p-value of 0.123451116, it's 5 zeros, is way less than 0.05, which is my alpha. So we reject the null, like very much so. Where mu1 is equal, or mu 1975 is equal to mu of 2014. Okay, we have significant evidence, or there's convincing evidence that the mean, I should say that the true mean number of hours worked by American adults in 1975 is different than the number of hours worked in 2014. Okay. So that was basically a whole significance test. We just broke it up into some separate pieces there. Here's your kind of definition again that shows you the test statistic and where it comes from. Find the p-value, use your t-distribution, use your degrees of freedom that are approximated by technology. That's going to be your better option, and all of that stuff. All right, so now let's do one of these from start to finish. We're going to do one more together, and we're going to actually carry out all 4 steps. So does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. Such observational studies do not establish causation. That's an important thing to note. Researchers therefore designed a randomized comparative experiment. Great. The subjects were 21 healthy men who volunteered to take part in the experiment. They were randomly assigned to each of 2 groups. Okay, so we're taking 21 people and we're assigning them to 2 groups. 10 of them received a calcium supplement for 12 weeks, while the control group of 11 received a placebo. The experiment was double-blind. Double-blind means the recipients and the person giving the treatment, neither one knows who's getting what. The response variable is the decrease in systolic blood pressure. That's the top number of your blood pressure. Your blood pressure has 2 numbers assigned to it. All right, so for a subject after 12 weeks, in millimeters of mercury, an increase appears as a negative number. Here are the data. So if their blood pressure went up, then it shows that it's a negative. Okay, so it says in part A, do the data should provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo, on average, for subjects like these ones, like the ones in the study. Okay, so we're just going to go through all 4 steps of our significance test here. We're going to start with state. We are testing. We want to test H sub O, where the mu for the control, or the mu for the calcium, minus the mu for the placebo is equal to 0. And our alternative is that the mu for the calcium group minus the mu for the placebo is greater than 0. We want this number to be positive. We want to show that there is a decrease in the blood pressure. And remember, they said that the negative result appears as an increase. Okay, an increase appears as a negative result. So we want a decrease, which means we want it to be greater than 0. We want it to be positive. Okay, where our mu C is the true mean decrease. See, we're already seeing the decreases here. We're not seeing the actual blood pressure, we're seeing the change. So the true mean decrease in blood pressure for healthy men like these in the study who take a calcium supplement and mu P is the true, I'm going to run out of room, mean decrease in blood pressure for men. Okay, I slid my little part up here so I had another line of space to write on. So where was I? The placebo group, mu P, is the true mean decrease in blood pressure for men who take a placebo. Like these in the study. Okay, so there's my state part. I almost forgot, I need to actually define my alpha level here, and I don't have a whole lot of room at the bottom, so I'm just going to come up here and write it at the top. So at the alpha equaling 0.05 level. Now, it didn't give us an alpha. It just said, do they provide convincing evidence? If you're not given an alpha, typically you're going to use 0.05. That's the most common one. Now I'm going to do the plan part. So for plan, I need to name my test. I am doing a 2-sample t-test for a difference in means for mu1 minus mu2. Okay. My conditions, so for random, okay, subjects were randomly assigned. To one of two treatments. 10%. Let's talk about 10% here. We don't have to list the 10% condition here. Because we took 21 people and assigned every single one of them to a treatment, we don't have to list the 10% condition. So now I'm just going to move into normal large counts. And counts. I can't spell today, sorry. So our n is equal to 21, which is less than 30. So we graph. When I draw a graph of my data, you have to draw two parts. So I have the placebo, I have the calcium, and I have the placebo. So I'm gonna have two lines to my graph. And my graph goes from about negative 10 up to almost 20. So here's a negative 10, and then a negative 5, 0, 5, 10, 15, 20. Okay, so I have two lines here. So I'm gonna do each one separately. For the calcium line, I'll just draw another line up here. I'm gonna use the same number line, but that's so I don't need to label the numbers twice. But I am gonna put both things on there. So for calcium, I'm at positive 7. I'm just going down my line here. Positive 7, negative 4, positive 18, positive 17, negative 3, negative 5, positive 1, positive 10, positive 11, and negative 2. Okay, then for the placebo line, I have a negative 1, I have a positive 12, I have a negative 1 again, I have a negative 3, I have a positive 3, negative 5, positive 5, positive 2, negative 11, negative 1 again, and negative 3 again. Okay, so when I take a look at those two graphs, the graphs reveal no strong skew. Reveal is what that meant to say. Reveal no strong skew or outliers. Okay, check. Good. All right, let's move on to do. Now we're in the do step. Okay, so we need to list all of our things. First of all, if it's easier for you, go ahead and put these two lists in your stat editor. You could put this into L1, you could put this into L2, and then you could do your one variable stats from there. And in fact, you're probably gonna have to do that because you need that standard deviation. And I don't know about you, but it's a lot easier for me to have the calculator find the standard deviation for me instead of me having to do the standard deviation myself. So I'm gonna go ahead and do that. I'm gonna type my group 1, the calcium group, in my L1. So 7, negative 4, 18, 17, negative 3, negative 5, 1, 10, 11, negative 2. Okay, so that doesn't take me too long. And then go ahead and type your placebo group into L2. Negative 1, 12, negative 1 again, negative 3, positive 3, negative 5, positive 5, 2, negative 11, oops, negative 11, negative 1, and negative 3. Okay. So now I've got those two things. Now I can go to stat, I can go to calculate, I can do one variable statistics, do L1, and I get an X bar for the calcium group of 5, and a standard deviation of the calcium group of 8.74. And my N for the calcium group is 10, which we already knew. Then if I do the X bar, so I'm going to go stat, calculate one variable stats, but this time do L2. Then I get an X bar of negative 0.27. X bar for the placebo group is negative 0.27. The standard deviation for the placebo group is 5.9, and I know N is 11. Okay, great. So now let's do the test statistics. So here's what my T would look like. T would be 5 minus the negative 0.27. You can put that in parentheses if that helps you. That's my mu1 minus mu2, and then I'm going to subtract the parameter, which is 0. We all know subtracting 0 doesn't really change anything, but it does show that you've acknowledged the parameter. In the denominator, I have 8.743 squared divided by 10 plus 5.9 squared divided by 11. And here's where I'm not even going to type that into my calculator. I'm going to go over to stat, and I'm going to do tests, and I'm going to do a two-sample t-test. And now I want to do data. So my list 1 is L1, my list 2 is L2. My frequency can stay as 1, and I'm switching my tails to be mu1 minus mu2 is greater. I want the calcium group to be greater. Pooled, I'm doing no, and I get a test statistic of 1.60. So there's my T value. So that means my P value is equal to 0.064, and my degrees of freedom is equal to 15.59. Okay, so now let's conclude. So in our conclusion statement, we have to say kind of two sentences here. We have to address the p-value and whether it's greater than or less than alpha, and whether that means we reject or fail to reject. And then we also have to put it into context of the question. So our p-value of 0.064 is greater than alpha equaling 0.05. So we fail to reject the null, where mu c minus mu p is equal to 0. So we're going to fail to reject it. So it says, then we put it in context. The experiment does not provide convincing evidence that taking a calcium supplement reduces blood pressure of healthy men like the ones in the study. All right. Oops, study. All right, there we go. There you have it. So state plan do conclude for a 2-sample test. Let's look at part B. It says interpret the p-value got in context of this experiment. So in part B, I would say something along the lines of, you always start with assuming mu c minus mu p is equal to 0. There is a 0.0644 probability of getting a difference of calcium minus placebo in mean blood pressure reduction for the two groups of 5, and then address that difference, 5.273 or greater, just by chance alone. Okay, so let's just take this piece apart a second. So we assume the null is true. We list the probability. We talk about the difference of what it is, and we state what that difference actually was. And our difference was 5 minus the negative 2.7. So it was 5 plus 2.7, which is where you get that 5.27. All right, that is our interpretation of the p-value. All right, so here's just a screenshot of what those calculator inputs look like. You can either do it with the statistics where you list the x bar and the s of x and the n for each one, or you can list the data, which is what we did in the previous example if you've got data in your stat editor. So that would be like if you had L1, L2, etc. Okay, this is the output that you get. They're just showing you a two-tailed test here. They're showing you a not equal to. Here's your test statistic. Here's your p-value. That's that p-value that I got. See the e to the negative 6. That's how I knew I needed 5 zeros in front of that 1 because I had to move my decimal point back 6 places. My degree of freedom was that 1,660.58, and then they show you the mean and the s of x again. Okay, so for pooled, they choose no, and we're going to talk a little bit about why in a second. Here's the data. If we use data like we did in the previous example, L1, L2, pooled is no again. You get your test statistic, your p-value, your degree of freedom, and so on and so forth. All right, so for an AP exam tip, it says, the TI 83 or 84 can be used to perform the test. In fact, it's more accurate. You get a better result if you use the calculator. However, the formula for a two-sample t-statistic for a test about mu1 minus mu2 often leads to calculation errors by students. Also, the p-value from technology is smaller and more accurate than the one obtained using the conservative method. As a result, your teacher may recommend that you use the calculator's two-sample test feature. Yes, I do. Your teacher does. To perform the calculations. Be sure to name the test. Be sure to report the test statistic. Be sure to report the p-value, and be sure to report the degrees of freedom. So if you are going to use technology, you need to still list all of those things. Using technology is great. You have to tell the test reader what you actually put into your calculator. That's a huge important thing. And then here's our little tip about a pooled population. It says most software offers the choice between a choice of two-sample t procedures. One is labeled unequal variances and one is equal variances. So the unequal variance, it says the unequal variance procedures use our formula for the two-sample t interval and test. This interval and test are valid whether or not the population variances are equal. So this will always work is what they're saying. This unequal variance part will work whether they're equal or not, okay? The equal variance is when you would pool your n values, but you only can do that if you know you have equal variance, and you don't always have equal. In fact, it's very rare for you to have equal variances. So that's why if you are doing this on your calculator, you don't want to use the pooled t, because your calculator will treat them as if they are unequal variances. And even if they are equal, it's going to get the best result, okay? So if you use a pooled procedure, that means you're assuming that you have equal variances, which is really rare. That doesn't happen very often. All right, thanks for tuning in. This was a good one. You guys made it to the end. So we're going to talk about a little bit more of testing for two samples in our next lesson video. That'll be the second part of section 11.2. But I appreciate you tuning in, and I will catch you next time.